Hello everyone, welcome to High Performance Computing Advanced Scientific Computing course, Lecture 8, Introduction to CFD. I am Reza, a PhD student, currently Professor Maurice, he is my supervisor, and my focus on the application of the high performance computing and machine learning in the computational fluid dynamics. I will take over in the second part of this course. Mostly we will focus on the application of the HPC in the area of the computational fluid dynamics, and we will have some introduction, and in next lecture we will have some practical lecture in this area. As we planned, lecture 8, it will be introduction to CFD, and we will talk in this lecture with two parts. The outline of the lecture listed here in the first part. What's the computational fluid dynamics? We'll talk about why we are applying the CFD and what's the range of the application. Shortly, we'll have a slide about the Navier-Stokes equation, and we'll point to numerical schemes. As well, in the second part, we'll talk about the classification of the flows, solution methods, and the procedure to make the meshing, the importance of the boundary conditions, and in the last talk we will point to most well-known methods in the turbulence flow CFD application, which colors LES and DNS. Let's start with introduction to CFD. Fluid dynamics is the science of fluid motion. Fluid flow is commonly studied in one of the three ways: experimental, theoretical, which sometimes we call it analytical method, and numerically, which is exactly computational fluid dynamics. Let's have a look on the antiquity of the fluid dynamics. In the literature, there are focus on the waterworks, aqueducts, canals, harbors, bathhouses. One key figure was Archimedes. He initiated the field of static mechanics, hydrostatics, and trigonometry. One of the Archimedes' invention is a water screw, which can be used to lift and transport water and granular materials. Here there are a few pictures and drawing from the history of the fluid dynamics. As well, here we can see the Leonardo da Vinci drawing for a gigantic explosion, which has a many detail and scale for the turbulence flow, and it's a very famous drawing in the turbulent flow area. Here these are pictures from windmill in Iran. That's from the studies. It seems they built in 1300 AD, and they are still available, and they are using by Aboriginal people for daily life. You can see this picture from 1932, and this picture from our time, which taken by some tourists. They went there and they visited the place. This slide included fluid dynamics from the past. This is the brief information from the past of fluid dynamic from 18th and 19th century, that we have very key figure Bernoulli, Euler, Navier and Stokes, which they built the equation. We call it Navier-Stokes now. As well, we had Lagrange and Rayleigh and Laplace, which they are very famous figure, and they made many important development in the fluid dynamic area. We have Osborne Reynolds. He did this important experiment, and he provide sight to see the difference between laminar turbulent flow, and then we have the Reynolds number. First part of the 20th century, We had many work on the boundary layers and turbulence. As well, we have the Prandtl number. We had the von Karman vortex state and Taylor, which is lead to Taylor microscale, and as well the Kolmogorov hypothesis and development from Batchelor. As well from 1881 and 1953, which life of the Richardson, he developed the first numerical weather prediction system. In which the part that is more connected to computational fluid dynamics and CFD in 1930 to 1950, the earliest numerical solution is done for flow past a cylinder in 1933. As well, in 1953, there is a numerical solution of the Navier-Stokes equation for flow around a circular cylinder at Reynolds number 4T, which is done by Kawat-Gotti. And to obtain the solution, he used a mechanical disk calculation working 20 hours per week for 18 months. This is a very interesting point, which we can understand how we can make with high performance computing and how we accelerate the solution. From 1960 to 1970, there are many developments in the numerical methods. There are many books, there are many schemes and methods to solve the numerical solution. There is a book in the numerical heat transfer and fluid flow from Professor Patankar, and this book, most influential book on the CFD to date. After this brief history, and if you are interested, there are many literature and resources you can look on it. Let's see what's the computational fluid dynamics. This example, simple example of the fluid flow inside the canal, which changing in the section. To solve this problem, we need sufficient grid in the size, which usually we call them sufficient fine, to solve this problem. There are different methods: finite difference, finite volume, finite element, and we will talk them in the next lectures. To find the correct solution, or maybe exact solution, we need to pay attention to the size of this grid or meshes to find the correct solution. Computational fluid dynamics, CFD, is scientific method to predicting fluid flow, heat transfer, mass transfer, chemical reactions, and other related phenomena by numerically solving the mathematical equations that govern these processes. CFD analysis produces engineering data that is relevant for various stages of product development, including conceptual studies of new designs, detailed development, troubleshooting, and redesign. CFD analysis is a complementary tool to testing and experimentation and can reduce the total effort required in the laboratory. Here is a picture. The source from NASA is the CFD images. There is a website. You can see this beautiful picture from some simulation. And this is the part of the beauty that is available in the CFD. Then why we are applying the CFD? Computational dynamics is the branch of the fluid dynamics, as we said before, for analyzing fluid flow with help of the calculation or computation. Usually, when we want to solve a engineering problem, we have three ways: experiment, as we said, analytical solution, and numerical solution. Experiment is possible for a specific problem. We have limitation of the measurement. It's required tools, which is most of the time is costly. there is a very complete dissimilarity in the scaling. So we can use the experimental result to validate the result on the numerical solution. So in this part, it's helping. But it's not possible to use it always for every size or every problem. The analytical solution is for limited and simplified problem, usually linear, very high computational cost, lack of analytical solution for many problems. We don't have analytical solution for most of the problem, especially the turbulence flow. But it's present general solution equation. However, it's not available for every problem. But when we look on the numerical solution, it's no limitation in solving if we are applying sufficient method, reduce the computational and operational cost, applied in complex problem, usually when we have complex geometry. Validation before the application, that means we can have a numerical solution and validate it and then we can apply it. There is two major issues. It's required boundary condition and initial condition that sometimes we don't have them, and we will look on this issue in next slide. Computing time depend on the computer power. This is exactly what we will talk in this course on the high performance computing. The numerical solution, of course, the best option rather than analytical solution and experiment based off the notes we said about them. But when we have large and complex problem, the computing will be costly. So we need high performance computing to solve this type of problems. CFD is comprised of math, fluid dynamics, and computer science. There are governing equations, which are partial differential equations. We call them PDEs in the CFD. They are broken down into a set of algebraic equations obtained by discretizing the equation into a certain number of the cells or points. We call them grid or mesh. Computer could not understand the PDEs, but the computer easily can solve the algebraic equation gained by discretizing. So the discretizing here is very important. To solve the problem, to solve the PDE, we need a method to make discretization on the domain of the problem. Applying the first law of thermodynamics and Newton's second law of motion on fluid particle will give us three sets of equations: mass equation, momentum equation, and energy equation. These three equations in fluid dynamics are collectively called as the Navier-Stokes equations. So far, we talk about what is the CFD and why we're applying the CFD. Let's have a look on some CFD application and why it's important in our life. The first picture here you see, it's an example of the CFD application in the geothermal energy, which was they making the drilling for the geothermal well, and they are applying the CFD to studying this type of problem. These two pictures here, they are presenting application of the computational fluid dynamics in coordinating spreading, the challenge that we faced in the last few years. And they apply the CFD to see how the COVID-19 is spreading and the social life to finding a solution. And there were many published work in this area, and they had very important and successful result. And this is a picture from the simulation for wind turbine energy. Now it's the challenge, and it's a very important topic in our time. Most of the countries and people looking for sustainable and renewable energy, which could be solar, wind, and other type. Wind turbine, it's interested in many communities because it's sustainable and has a good efficiency. So there are many efforts to applying the CFD to make a simulation and studying the wind turbine. The next picture is the example of the using CFD for aircraft, which is the most application and oldest application for the CFD when it's born to using in aerodynamic area. There is the example of the application on the health and medical science. The next picture is the CFD application for SpaceX Dragon, which is simulated the spacecraft. The next one is the simulation for CFD for aerodynamic around the car, which is also one of the oldest application in this area. So we have the CFD application in automobiles, spacecraft, medical, and aircraft, which has a very different application and different area in every category. From the previous slide, we understood that application of the CFD is broadly and it could be applied in many different areas, from daily life to very complicated industry. There are many websites contain information about the computational flight dynamic. CFD online has a collection of the information. NASA site has a very nice images from the CFD simulation, and you can see many different areas. Here there are two examples from them. E-fluid as well has a large number of the fluid mechanics material, and there are some new books published as well. It's coming there, and some of them sometimes open access, and you can have access to some resources. This picture is isosurfaces of Z vorticity shed from a cylinder simulated with Phone 3D DES, which is a specific code. It's running by NASA Langley Research Center. And as well, this is another example of the blade wakes, which is simulated. CFD codes. To apply the CFD, we need to have codes of solver to solve the problem. There is two main categories, commercial codes and open source code. The commercial codes like ANSYS Fluent, Applied Computational Flight Dynamics, Azure, Fluidine, and etc. From the open sources, we have OpenFOAM, Calculix, CANS, Dolphin, FluidSim, and etc. The most important and difference between these two types of the code, the commercial code usually used in the industry, and they are limited to the change. That means we can change the algorithm and structure of the code to have a very specific problem. But for open sources code like OpenFOAM, the source of the code is open and accessible. So if we have a specific problem, we can change the algorithm, and we have different solver for a problem. Therefore, the open source usually used in the research application. Here is the screenshot from the Newton supercomputer, and you can see we have module for ANSYS Fluent. Usually the CFD codes and software includes the solver, the grid generation software, and flow visualization software. Regarding the open source codes for CFD, As I mentioned before, CFD package can accurately solve simple flows but are designed to handle complex geometries and industrial problems. They are valuable design tools when used by a knowledgeable user. Commercial CFD codes may not be suitable for state-of-the-art research due to accuracy limitation and limited user access to the solution methodology and code customization. So if we are doing research, we need to open source code like OpenFOAM. And there are other codes using in the Euro project recently, since we are collaborating in the EU project, EuroCC, CORAIS, and some other project. So we have some other codes it's applying currently in the use cases in the CFD. You can see this information here, and there is a source. You can read about them, and you can see how they are working. Regarding the computational resource, CFD is a multidisciplinary topic, as we said before. We have numerical analysis, fluid mechanics, and computer science, and all of them together making the CFD. The computation of fluid dynamics had traditionally been one of the most demanding computational applications, driving the development of the most powerful computers. If we wanna mention the computers, we had the single processor computers, then we had vector computers and parallel computers that now we are using shared memory and distributed memory. About the detail of the computation, we will have lecture on the parallel computing and we will go in detail in this regard. But so far, we understand when we have a massive problem with many grid and nodes, we need computational resources. And usually here, the HPC is the key solution to be able to solve very large problem. If we don't have the parallel computing and CFD, it's impossible to do that, especially in the turbulence flow. However, when we talk about the computational dynamics, it's not only on the fluid area. We have another area which is called multi-phase flow. That means we had a flow with two state of substance like gas liquid, sometimes solid liquid, and sometimes solid gas. So the numerical simulation in this area it's important, and it's one of the sophisticated area of the studies. In this slide, there are some picture you can see. This is the DNS solution of the gas liquid multi-phase flow books here, and this picture is the example from simulation of this spherical buoyant bubbles in the flow. We have the splash, we have the atomization, we have bubbly flow, and many examples of the multi-phase flow. You can see the listed of the multi-phase flow, spray drying, pollution control, pneumatic transport, slurry transport, and many other examples. So the CFD is playing the key role here in this area to solve this type of the problem, and as I said, is one of the most sophisticated area of the CFD. The other area of the CFD is the combustion. There are many research and studies using the CFD in the combustion to simulate the combustion. For example, the combustion in the engine of the car, or any type of the flame on combustion. There are many different type of the study. Regarding the combustion, we have the gas combustion, gasoline engine, gas burner, spirit combustion, jet engine, diesel engine, combustion of solids, coal, wood, polymers, uh, and one of the type of them is the diffusion flame. In general, combustion is a highly intricate process that involves over 100 species and reaction rates. While the reaction rates for several reactions are reasonably well known, combustion remains an open research field in general. So CFD as well here is the main application that could be held to solve some research or industry problem. For example, one of the state of the art in the combustion or applying hydrogen as a fuel to create energy, and the flame on the hydrogen it's studying now. And there are many other examples in the combustion which is only possible to study via the CFD, and there is not analytical solution. And as well for the experiment, for example, when we are speaking about the hydrogen, it's very dangerous to have an experiment with hydrogen. It's needing many control and safety to make it. Therefore, they prefer to use the CFD in this area. Let's have a look on the Navier-Stokes equation on the CFD. Since we are not going teaching the CFD in this course, as we said, we only have a few lecture introduction for the CFD. And then we just point to the available equation. The Navier-Stokes equation is governing for Newtonian fluid in compressible flow. There are second order nonlinear partial differential equation and quite formidable. And you can see how it look like the equation. In the fluid dynamic, we have two types of the regime of the flow. We call it laminar and turbulent. You can see in these two drawing, the first one is a laminar flow. You can see the flow, it's moving in the uniform behavior, and you can follow every streamline of the flow. But the second one, the turbulent flow, as you can see here, it's a very non-linear, and they don't have any pattern and random motion. So this is one of the biggest challenge in the physics, more than 1 century, and still open area of the research. In the CFD application, we are using these numerical methods to solving sometimes turbulence flow, which is one of the most CFD problem that need a parallel computing and hyperparameter to be possible to solve. Regarding the numerical method, we have the finite difference, finite volume, finite element, spectral element, spectral method, boundary element, reduced method. All of these numerical methods applying to solve the Navier-Stokes equation for a specific problem. This equation have four unknown: pressure, three components of the velocity u, v, and w. They should be combined with the incompressible continuity relation to form four equations in these four unknown. The Navier-Stokes equation have only a limited number of non-analytical solutions, so we need to do numerical solution. It is possible now to achieve approximate but realistic CFD result for a wide variety of complex 2- and 3-dimensional viscous flow with help of the CFD. So the CFD makes possible to solve this type of the equation that doesn't have analytical solution. So far, we talk about the available numerical methods that they are applying in the CFD. What is the difference and what the advantage and disadvantage of these methods? We have the finite difference method, which is simple, straightforward to apply, usually for a regular grid. Next one, the finite volume method, is usually for irregular meshes grid. And the third one is the finite element method. It's for structured and unstructured grid, most difficult and sophisticated computation. FEM solve any problem with differential equations. It is complex method. Here, few examples we can see. In this example, the meshes are, we can say, they are structured. They have a very straightforward pattern to solve. This type of the mesh or grid, we call it structured. But this one, we can see, we have to, in some areas, we have very small meshes and grid, which usually we say we need to have a fine grid on here in this area. And other area, they are very different size and larger meshes. This type of the mesh is unstructured mesh. This is the example how we are applying the finite volume method or finite element method. Usually we create the volume of the element and we find the properties of the feature in the center of that value. So there are different methods. We will talk about them in the next lectures. How we are applying the finite volume, how we are applying finite element method to solve the problems. This is the last slide from the part 1 of the lecture 8, which is Introduction to the CFD. This video presenting industrial application of the CFD for the aircraft aerodynamic performance, and you can have a look on this video on the YouTube, and it provides you information how CFD applied in this area, and why in this size of the problem we need the high performance computing to solve this problem and make development in the aircraft which make the flight safer and the life with more safety, and you can enjoy your travel. Same of this area in the other areas as well. Application of the CFDs make development and comfortable life for the human. So the application of the CFD, it's essential, and beside of the CFD, we need to have parallel computing and high performance computing to do that. In next lectures, we will talk about the parallel computing. However, I leave you in this slide for a few minutes, and after the short break, we will back to continue this lecture on the part 2, and we will have some more discussion about the CFD. Thank you.